right? Yeah. The answer is yes, right? Okay, so now what type of connections? What type of connections are there when we talk about them? There's three types. Who can remember what they were? Anybody? Fixed. Very good. Fixed connections. Or we call those, what was the nerd word? Fully restrained. Right? But we've often used fixed. But they're the same thing. What other type of connections do we have?
A pin, and then you have a spring.
A pin and a rotational spring. Very good. And I'm glad you responded that way. That's how I'd respond as well. But if we talk about what AISC uses in maybe a little bit more academic terms, they would call a pin connection a simple connection. And they would call a spring a partially restrained connection. So, you have to be really political. Well, I don't know if you have to, but these terms seem to become very political. People start to use them more and more. Now, when you think of a pin connection, what qualities usually do you think of? What do they look like? What's a pin connection look like? Who remembers? What are some things that usually happen in pin connections? Well, maybe it's a little too complicated. Let's talk with fixed connections. When I say something is a fixed connection, what do you think of? What's something that comes to mind? Well, what do we know fixed connections have to do? What do they have to be able to do? What qualities do they have to have?
They have to be able to take moment.
They have to be able to transfer moment. And what else do they have to transfer? Shear. Moment and shear. So if I have a connection, that's exactly right. If I have a connection, let's say I draw a W shape. Where in the W shape do I usually think of my moment being? Think of moment. What do I usually think of? What stresses? And where are they?
Flange.
Flange. And they're tension and compression, right? Tension and compression. So, and then when I think of shear, what do I think of usually? Web. Okay? So we got our shears being transferred by our web, and our flanges are transferring our tension and our compression. So a fixed connection has to provide a load path, at least conventionally, the way we've thought about it in the past, has to provide a load path from the top flange to something else, from the bottom flange to something else, and from the web to something else, right? That's what we usually think of. And when we think of a pin connection, what loads do we think of being transferred? Shear. Right. So when we think of a pin connection, where do we have to have our load transfer at? The web. That's right. The web. That's where we have to have our load transfer. Okay, so what's a partially restrained connection? What does it do? This is the part where everyone starts getting nervous and they don't really know, because what's a partially restrained connection, a rotational spring, and well, the answer is it's in the middle. It still has to transfer shear, but it's able to transfer some moment. Maybe not as much moment and be as stiff as we would think of for a fixed connection, but some moment. So I've kind of already explained to you in words, and I think you could have too if I really would have pressured you, and you would have come up with the same answer. And so you already know where we're going. You already know what we're doing and where we're headed. And now we're just going to talk about a little bit of math to help convince other people sometimes on what connection you're going to be using. Right? So yes, that's what all these things look like. And then I asked this question, how does AISC classify connections? Because they don't want to just look at these things, because the question comes in that the weirdness, the in-betweener, the thing that's hard to categorize is what happens when I have a W shape that's connected to something else that's really, really deep. I mean, we're talking crazy deep. crazy deep. I mean, maybe it's 6 feet deep or something like that. And I have some kind of bolts all along that 6 feet. Okay? Let's say it's a splice between 2 girders. Perfect example. The girder's here too, and I have connections here. Bunch of bolts. Oh my gosh, I can't even draw all the bolts that are there. And obviously, we'd like to have the same amount of plate on both sides, but you'll forgive me for that, right? Today, okay. Thanks, I appreciate it. So we have a lot of bolts, but we're not connecting our flanges, and it's super deep. So what would you consider this? What would you classify this? Well, some people would say pin. Why would you pick pin? There's not a direct path, and that's kind of what I've beat into your head to do to this point. But could you squint your eyes and see that, you know what if the load did this? Is that possible? And what if the load did this? Is it possible? We're not asking likely. We're not asking would you count on it. We're asking, is it possible? And then I think the answer is yes. Undoubtedly, the answer is yes. It is possible. And if you wanted to, because if you talk to those guys and if you listen really close, those WW Steel people, they would say things like, well, we would usually do this with a fully restrained or a full penetration weld, but we beefed up the plates and we got away with doing it with a partial penetration weld. They're doing those things to try to save money. And if I can keep from putting a plate here and a plate here and making that connection, I can save money. Is everyone with me on that? Now, would I want to do that every day of the week? I don't know. I agree with what Jennifer said earlier. If you just assume it's a pin connection, then everyone's life is so much easier to do. All the risk is so much less. Sometimes that's not the goal. Sometimes the goal is to save money. You with me? Again, this is the class where we start to work on harder problems, more challenging problems, all right? So I think everyone would agree that there is a possibility you could transfer moment in this connection. It's possible, if it's deep enough. And you could count it as some kind of, well, would it be full moment? Would it be a partially restrained connection? Or would it be a pin? Well, the math will tell us, and that's what we're learning how to do. The math will tell us. You with me? Awesome. Now, telling you, if my PE is on the line, if it's something that I care about, and I'm not involved, like I don't get extra money because I save someone money, I'm going to assume it's a pin every day of the week. Okay? But design build is the future. Okay? It is the future. Design build means the same group that designs it is the same group that builds it. And there's a huge interest then to save money. Okay? Save money on these type of connections and take more risk, more calculated risks. Does that make sense to everybody? Great. So now, how does AISC classify a connection? We talked about this last time. I know it's been a little while. How do they classify connections? Oh, I've already given you hints. They draw graphs. They love graphs. They love math. Okay? They like things you can calculate. Okay? And on one graph, one axis they have end moment, and the other axis they have end rotation. Now, what do we draw next? Who remembers? What was next? Well, we had some lines, right? We had some lines we drew on there. And what were the lines at? One here and one here. Okay, now we're going to see this graph over and over and over again. It's time to memorize it. It's time to remember it. It's very likely I would put this on the exam with holes in it where you have to fill it in yourself. Okay? And what we have these things labeled. I heard 2EI over L. Yeah, 2EI over L. And that's actually the slope of the line. That's the slope of the line. And we had 20 EI over L, and that's the other slope of the line. And we have moment on one axis, and we have end rotation. And then I had some other lines that I drew on last time that probably weren't clear. One line was really close to here, and this is what? What was this? And I had another line down here. Another line down here. And this line had a label as well. Who remembers? Who could guess? Fixed. Fully restrained. We'll call it FR for fully restrained, right? Or fixed. Fixed is actually probably even a better answer, Jacob. Purely fixed. The pure academic fixed. And how about down here? What was this? Pin. The pure academic pin. Okay? Now, and we all realize we've used these things forever and done these things forever, but in reality, there is no such thing as a fixed connection. So, structural analysis, believe it or not, has been lying to you. You probably already believe that. Okay. And pin, every time you've drawn a pin, they've been lying to you. Now they're pure lies. They're true lies. They're ones that have the best intentions in place. Okay? And they're not that far off, all right? But they're not purely right. Okay? Kind of like Santa Claus. You know, there's good reasons why we do it. Right? There's good reasons. So you can go talk to Santa Russell, right, and tell him that there's good reasons. We come up with different quadrants and zones, okay? Good zones, and these zones, this is where we call the simple connections. They're same zones we talked about before. This is what we call the fully restrained connections, and this is what we call the partially restrained connections. So if your connection falls in one of these zones, that's what you can. Can is the key word. It's what you can classify it as. And remember, if we're dealing with prismatic members, what does prismatic mean? Prisms. Has something to do with prisms. Right? What's prismatic mean? Who knows? Oh.
I mean, it's got the same cross-section.
Very good. Thank you. It's got the same cross-section throughout. So if you have the same cross-section throughout, it is always conservative to assume a lower amount of stiffness. If you do not, it is not always conservative to assume the same cross-section throughout. Okay, so if our connection happens to end up in this zone, guess what? We can call it fixed. If it happens to end up in this zone, guess what? We can call it rotational spring if we really want to. And if the connection falls in this zone, we're required to call it a simple connection. You with me? Now I have this one connection at the end. So this is real important, super duper important. Either the concepts or the graph will be on an exam or final quiz. If I sing it, it makes it more fun, doesn't it? Okay. So then I ask this question. Do connections ever change classification? Do connections ever change classification? Yes. What's the example? When they slip. What's another example? Yielding. Great. Awesome.
What if they corrode?
Ah, very good point. What if we have durability issues? What if we have fatigue issues? All are very true statements where connections may lose. Now that's what our inspection's for, right? We inspect these structures. But those are all possibilities. All good possibilities. Okay. So yes, they definitely change. And that slippage, corrosion, fatigue, yielding could be any reason why you'd be running along on a certain line and you think you're all cocky and, I'm a rotational spring. And then all of a sudden, boom, you fall. And you might still move along at a similar stiffness. But it's too bad. You've fallen in the quadrant, and you are a simply supported connection. You with me? Great. Great. We talked about some of these connections in detail, but really we had gotten and reached this paper, right? Yeah? We had reached this paper last time. Now what we're about to talk about is hard. And what we're about to talk about is something that you have to dive in, and you have to probably spend some time on your own to review to understand what's going on. Okay? Because we're going to be looking at this problem in lots of different ways that you're not used to doing. And you're going to want to memorize the one way to do it that I showed you, and the one way we use it. And guess what? We're going to ask you to do things differently when it comes to homeworks and exams. So the key to learn here is to understand the process, not necessarily the details of what we're doing. But what we're fundamentally going to try to do is we're going to try to solve this problem. We're going to try to solve for a deep girder. We're going to try to solve and say, what section am I in? Am I stiff enough to get fully restrained? Am I loose enough to be simple? Or am I somewhere in the middle? Okay? So we're going to try to understand. And now, to do that, we're going to have to take our structure and we're going to have to do things a little differently. And I'm going to be explaining a process of what we're going to do, and then where there's an actual work example problem where we do it, and hopefully between the two, it'll make a little more sense. And after the homework, hopefully it'll make a whole lot more sense. Okay? Now, what we have to realize is that we have to start thinking about these connections a little differently. And when I showed you a connection like this, what is your first impression? What would you assume it to be? What would you model it as? Pin. How come? There's no load transfer, isn't there? There's no load transfer. So you would assume that it's a pin, right? And I think that's a fabulous. Don't do away with any of that, all right? But now we have to change our mindset a little bit, and we'd say, maybe it's a partially restrained connection. Maybe it's fully restrained if this plate's thick enough and it's deep enough and there's enough bolts. Maybe, just maybe. Maybe. And you have to believe in that. You have to say that that's maybe possible. And let's do some math to figure out if that's right or not. Okay? That's what the mission we're about to embark on. So now what we're going to do is we have to think about, okay, my gut tells me it's simple. I'm still thinking it's probably simple, but now since we have a shear on it, I'm going to say, you know what, I'm going to imagine that it could be a moment connection, a partially restrained connection. Okay? I'm going to imagine that it could resist moment. And I'm going to imagine that when this shear comes through here, that the shear is going to go through all the bolts, and that now this is going to be my moment arm. Does that make sense to everybody? And then when the load transfer happens, the load transfer is happening up here, and the load transfer is happening down here, the moment load transfer, and the shear is going to be transferred in the middle. Now we're going to assume shear is going to work. It's just another check. It's not that big of a deal. Okay? Shear is a check you'd have to do no matter what the connection was. Everybody with me on that? We did homework on that. Okay? Now we're really wondering, do we have the stiffness and the load capacity for this couple? That's what we're trying to work on now. So now what we're going to do is we're going to imagine the worst. We're, in a sense, if we go back to our diagram, and what was the y-axis on the diagram? Our key diagram that decides everything? What was it? It was what? End moment. End moment. Moment at the end. And what was our x-axis? Rotation. Rotation. What I'm going to imagine here is that And I could actually pick any point along the line. But what I'm going to pick a point that's easy. Okay, I'm going to pick a point that's simple. What I'm going to imagine is that I'm going to start at the origin here. And I'm going to imagine that I increase linearly up until some critical point. What do you think that critical point could be? Yield. Yield of what? What's that? Yield of what? Yield of the angles. Yield of the angles up here. That's what we're gonna go towards. All right. All right. And we're gonna calculate the point right before yield. We're going to actually now. Please realize that this is probably not linear. Okay. This is probably not linear at all. It probably looks something like this. All right. And we are just going to assume 2 points and draw a line. Yes, sir.
Is that assuming that both types of steel are the same, or one stronger than the other?
What do you mean by both types? What steel?
The angle steel that you're attaching to in the web, are they the same with steel? They're not, but two different yields.
Sure, they are. They are.
We're in your web than you're in your angle.
Sure. And I understand what you're saying. The check of the member is a separate check. And we're really doing a check of the connection right now. Now, if you notice, though, and you won't until you do the homework, it's okay. People don't ever do it. But when you do this 20 EI over L and 2 EI over L, those lines, the E and the I that you use and the L that you use is of the member. It's of the member. Okay. It's of the member. So now we're going to do something like this. And we're going to change this really complicated equation. And if you ever have lots of money and you want to pay somebody like Oklahoma State to test a connection for you, we would be happy to do that. And people with lots of money do that. Okay? Seriously, it's common. Okay? But instead, you can mathematically calculate about 3 points on the graph. Kind of get a feel for it. All right? But sometimes people will actually require you to test a connection. And actually in Australia, they have a whole book of connections. It's like shopping. You know, it's like now we shop online, and the book's probably online now too. But back in the day, you know, when we used to, come down at Christmas, you get the catalogs out, you start circling what you want, you know. Well, they actually have a whole catalog of connections in Australia where they have done a whole bunch of tests, and they can tell you, use this connection, and it's good for this strength, and it's good for, you can model it as this. It's all been done for you. So everyone likes to do their own thing here in America, though, right? And we instead have to do calculations. Okay? Okay. So we're going to go for this point, and then we're just going to assume it's flat after that. You with me? Everybody with me? Okay? And we're going to see what zone we end up. Do we end up here? Or do we end up down here? Or do we end up here? You with me? Okay, so that's what we're going to do. So just like we said, we're going to be looking at movement and yielding of the angles. So we're going to actually allow this to deflect. We're going to allow it to deflect. We're going to allow it to bend and move up until we start to get yielding. And really, I probably should have a picture that looks something like this on the page. We're going to allow this to happen. And we're going to calculate the load and the rotation when yielding occurs up at the top. You with me? Yeah? Okay. So now we've got to model that. We have to take something that's obviously a very complicated connection, and we have to make it something that we know how to do. This skill that I'm talking about right now is crazy valuable, okay? You sing it, right, then it's good, right? It's really valuable, okay? And if you can learn to do this, you can solve a lot of hard problems, okay? But it's what you do is you say, you know what, I'm just going to zoom in here on the top. I'm going to think about what A looks like. Almost if my eye is on top of this looking down. Okay? A plan view, a cut right through there. And really, it's going to come down to what my connection looks like. What my connections look like over here. Do I have bolted connections? These are supposed to be bolts, bolt, 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 bolt. Or do I have welded connection? This is weld, 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 weld. Believe it or not, that is going to change everything. It's going to change everything. Okay, that's good. You're believing me. Nodding your head. That makes me feel good. Because if I have a bolt and I draw the deflected shape, again, I'm drawing the deflected shape of this material, the top of my connection. If I draw the deflected shape, the top is going to look like that. You with me on that? Here's the web. Here's one part of the angle. Here's the other part of the angle. Notice that it doesn't really matter what this connection looks like. Doesn't matter if it's bolted. Doesn't matter if it's welded. It's just there. Okay? But this does matter. If this is bolted, we're going to get some squeeze. We're going to get some localized restraint caused by the head of the bolt. And if it's welded, we're not. It's going to just pivot and rotate. Now, have we ever seen any kind of connections that we know how to deal with where it has this almost zero amount of rotation and then almost zero amount of rotation? We've seen that before? Yes, we have. It's a fixed connection, isn't it? And have we ever seen a connection where the rotation, when I say rotation, I mean this rotation, is whatever I want it to be, whatever it wants to be. And it's flat, and it's down here, and it's whatever it wants to be again. We've seen that. And that's a pin connection, isn't it? So if we know how to draw the deflected shape, we know what the critical behavior is, we can actually capture that and come up with a much more simplified model. Being able to go from this to this is worth a lot of money because you can solve a lot of really hard problems. Okay? Now, when I showed you this problem, you probably said, oh my gosh, I have no idea how to do this. And now when we simplify it, look like this. Now I have a fixed connection. Now I've drawn a infinitely rigid beam in the middle. Why did I do that? Well, we really do have that in a sense. We've got a super thick web. We've got a super thick flange here and a super thick flange. And is it truly infinitely stiff? No. But it's way more stiff. You have the singing again, right? That's why it's important. It's way more stiff than this. Right? Way more stiff. So we're going to call it infinitely stiff. You okay with that? Now, I don't really not used to dealing with things that are infinitely stiff, but since it's symmetric, I can actually simplify this. And I say this infinitely stiff area is equal to 2K plus the thickness of the web. What's K? That's not exactly the angle thickness. It is actually the depth from the edge of the angle to the end of the chamfer. That's what we call the K distance. Okay? That's what we call the K distance. It's from the end of the angle to the edge of the chamfer. Okay? That's what we call the K distance. And if we remember, the chamfer's there because these sections are rolled, right? These are rolled sections. So when they come out, there's a non-uniform thickness right there. Now, is the K the perfect place to take it? Maybe not. Maybe if you're doing this problem, you want to do it from here. This is one of those judgment calls, okay? It makes engineers nervous. Makes them nervous. They don't know what to do. Where do I call it? Obviously, I wouldn't want to call it here at the center. Right? I mean, that's not right. And obviously, it's somewhere between here and here. You with me? And believe it or not, it doesn't really matter which one you pick. You'd say, oh my gosh, but that's going to change my answer. Okay, do the problem with different decisions. And see how that changes your answer. See how sensitive it is to that decision. And then make something conservative. Does that make sense? Yeah? Okay. So. I'm going to pick here. I could just as easily see someone pick here. I could just easily see someone pick someone in the middle, the 2/3 point, whatever. Pick one, document it, and go. And if it keeps you up at night or worries you, go back and address it. Go back and look at the range. Does that make sense? That technique of bounding the problem, picking an answer, and then go back and check it, is something we're going to be doing over and over and over again. It just won't always be applied to the K factor, okay? It may be applied to all kinds of other things. Okay, so we got this thickness, and we're going to imagine like it's not there. We're going to simplify the problem even further to this. How can we do that? Is that conservative? Is that okay to do? It is. The reason why is things that are infinitely stiff, they're pretty strong, aren't they? So we wouldn't expect any yielding to happen here, would we? We'd expect yielding to happen here and here, or here and here, right? And we care about deflection, don't we? Remember, we care about moment, we care about rotation. So we care about deflection. And rotation, is this gonna bend? No, it's not, because it's infinitely stiff. So this is going to be the main contributor to our rotation, as you're going to see later on. And it doesn't matter. This is the same in this problem as it is in this problem. Now, I've just thrown a bunch of money your way, believe it or not. Okay? I've just given you a cool way to go from some very complicated, hard problem, simplify it into a simpler problem, it's still a hard problem, and simplify it to something that you've been doing all of your life, well, all of your structural engineering life, right? That's what you need to learn how to do in this class. You've always gotten away in the past with a simplified version. It's not going to be that easy, okay? Now, we do the same problem for welds. Everything's exactly the same, except for I only have pins at the end instead of fixed connections. Now, how does that change things? Well, the load it's going to take to make this deflection happen is going to be different with the pins than it is with the welds. So my deflection equations are going to look somewhat different. Is everybody with me? Awesome! Now, we have a way to quantify rotation of our connection. As our loadings are increased, we can also modify our connection if we need to get the desired fixity. What I mean by that is, if we're not happy at the end with what quadrant we end up in, we now have a quantifiable way to come back and say, well, if I want to make it fixed, then I have to make my angles this thick. In the past, you looked at it and you'd said, oh, that's simple. That's a simple connection. But you didn't, if I would have said, well, how could you have made it a fixed connection or a partially restrained connection? You would have told me you put something at the top and the bottom, and I said, but you can't add any other members to it. Now you have to work it this way. You with me? Awesome. We assume this rotation is linear until we get to yielding of our connection angles. And that's really just explaining, this sentence is really just explaining this. We're going to assume, we really realize that it's this nonlinear performance. And we're going to assume we're going to do a single linear line, and then we're going to do it, it's going to be bilinear. It's going to be elastic plastic. That's our assumption. You with me? Okay. And if you want to spend 2 weeks on a finite element program, believe it or not, you can trace out the true behavior, but I'm going to get the same answer in about 10 minutes on 3 pieces of paper. Okay, so now let's work an example problem. And we're going to basically take everything we've been talking about and we're going to put it into practice. We've got a connection. I've got some bolts here. I've got some welds here. Telling you what the angle size is. Telling you the grade. Telling you what the size of the beam is and the load. I ask, what is the classification of the connection? I also gave you the beam length. So what is the classification of this connection? So we're going to go through this process. We're going to first assume that the connection will have some rotational stiffness. Hey, that's just what I told you to do. Assume it's got some bending moment. Let's find out the moment when the angles will yield. Hey, that's our original geometry. We're going to say we're going to allow some bending stiffness to occur, some stresses to happen like this. We're going to get some loads that happen like this. We're going to get some deflections that happen like this. You with me? And we're going to stop it right when it welds, or right when it yields. You with me? Okay. So here's my plan view of my connection. Here's my simplified structure. There's my load on it. There's my moment diagram in the angles from a pin, because why are these pins? Because they're welds. But I have bolts here. They don't matter. They don't matter. What matters is here. Okay? We have welds, we have pins, we have this rigid area in the middle, we put this load on it, and we're going to get a moment diagram that looks something like that. So where is the yielding occurring at? In the angles, and where at? Right here and right here, isn't it? Yeah? Where is it occurring at up here? Top or the bottom? The top. Good answer. Now, here comes the hard question. You okay with that? The top? Here comes the hard question. When are we going to stop? How much are we going to allow to yield? Are we going to allow... Well, that's the stress diagram. You guys are all with me on that, right? How much do we want to allow to yield? Do we want to stop right when the very top fiber yields? That'd be kind of cautious, wouldn't it? Some people don't know. I think it's pretty cautious. How about the whole thing? We're going to allow the whole thing to yield? Some people don't know. Probably not. So how much? Just enough to make it. This is the part where in the class there's no right answer. What I'm trying to get at here is that if I only allow the top fiber to yield, then as soon as that yields right there, we'd have to stop. If I'm going to allow the whole thing to yield across the cross section, I'm going to allow that all of that to yield when I stop. That's not safe. That is wrong. I'll tell you that right now. That's dangerous. Now, how much do we want to yield? What's that? 5 to 10%. It's as good as answer as any. 5 to 10% of what?
The distance from the top fiber to the middle.
Okay, you could take from the top fiber to the middle. I think you could probably get away with the entire depth. Now, that's an individual engineer's decision. And again, I told you this before, but when we get very hard problems that we don't really know how to solve, we don't really know the right answer to, and we don't want to spend 2 weeks on the finite element package, what do? We bracket it. We found the problem. And in a sense, we did. We said, we know that's too conservative. We know that's too liberal. We want to be in the middle. And now we start checking. We start getting a feel for the problem. We start saying, okay, 10 to 15% of the depth, of I think the total depth. So that would be saying we'd allow yielding to happen. I think this is 16. It's the total depth of the connection. Okay, that would say that we're allowing 1.6 inches to yield. So half of this space in between the bolt and the edge would yield. It's a great place to start. It's a fabulous place to start. Let's say you get an answer, work it a different way. You work it again now. Instead of 1.6, you assume 3. See what you get. Assume 4.5. See what you get. Get a feel for what's going on. Because in a sense, when you do that, what you're going to be doing is you're going to be tracing out this curve. You're going to be getting different points on the curve. And it's going to get to a point where it's not going to matter the depth you choose. Well, there's this area in here where it doesn't matter what you choose. Because if you draw a linear line, it doesn't really change that much, right? The slope of that line doesn't change that much. But if you choose something over here, that's not going to work. You with me? All right. Welcome to Advanced Steel. This is what we do. Okay, so we got this problem. This is what it looks like. We got the rotation. We've talked amongst ourselves at least about this depth, and we came up with the answer around 5 to 10%. I think for the example problem, I chose an inch. Okay, an inch, which is right around 5%. It's around 7% total depth. It's just a number I chose. Don't always choose an inch. Don't just because I did it in the problem. Have a reason. People are still going to do it. I know they are. So now what we're going to do is we're going to basically try to work this problem. We're going to really, in a sense, try to work this problem. Do you know how to find the moment for this? Sure you do. It's easy. It's just peel over 4. It's the moment for that. Okay? Peel over 4 would be the moment here. Then you'd have to back it off to wherever the edges of the member are. It's not that hard though. Okay? So I go, let's find the point where the angles yield or form a plastic hinge. So what we're going to do is we're going to say sigma, the stress, is equal to my over I. And when I talk about sigma, I'm really looking at this equation, this bending diagram. That's sigma. I'm finding where that sigma, that is equal to my over I. And I'm going to solve for my moments. Because I'm going to have an external moment. How do I find that? That's easy. 150 kips times what? 3 inches. Right? 150 kips times 3 inches. And it's got to be equal to what? My internal moment, right? Or it's got to be comparable to my internal moment. So I'm solving for an internal moment now. So to find my internal moment, I have I over y times Fy. And I use 36 KSI. And I solve, well, and then y. What's y? Well, I say it's 5/8 over 2. Just realize what we're talking about here. We're talking about this member bending and failing. So when I talk about this cross section, I'm talking about cutting it so that the depth, this is the depth. This is what we would call the H, right? Right? This is the hardest part for people. And what's the B? It's the distance into the page, isn't it? What do we choose for B? Well, it's that depth that we're allowing the yielding to occur over. Our B is this depth that we're comfortable with, that we're allowing yield to occur over. Our B is our depth into the page here. Our H is our thickness of our angle. Okay, so I don't know how else to say it. You're just going to have to look at it so that makes 100% sense to you. We're going to have a 1/12 BH cubed calculation here. And I'm going to choose 1 inch as my number. And again, that's like around 7.5% of my total depth. Okay? And my y is going to be 5/8 over 2 because it's what? It's half my depth, isn't it? It's a rectangular cross-section. 36 KSI. And I solve, and I find out that that requires 2.28 kip inches. Is that very much? Nobody knows. Okay, fine. So, this is the moment in the angle that is needed to cause yielding. Let's find the force in the web needed to reach this point. Okay, so we've got this moment that we can resist. Got the moment. Now we've got to find the force. Okay. So we're going to take this, we're going to simplify it to this. We talked about that earlier. Now my moment's going to be PL over 4, where my L is equal to G. And I'm going to back solve for P. Just do a little algebra. I'm going to plug in here 4 times my moment, which is 2.28 kip inches, which I got from up here. Oh, I think my time is over. It just kicked me off. So we'll start again right here, all right?